Recording. All right. Hey, everybody. I know it's been a while since I made a video before, or since I made the last one. I'm sorry about that. I'm going to try to make ones more frequently. One of the questions I get asked a lot is, what do we do with the, after we run DIA-NN or Spectronaut or something, how do we do differential expression, or how do we know what's changing in our samples and our different conditions? I have a good video on this using MSDAT, but I thought I would show you my current favorite software for doing this, and it integrates really nicely with DIA-NN, and so all of this is free. This is a new software project called Limpa, and this is out of the Gordon Smith lab, who also did Limma. And so Limma is one of the tried and true differential expression packages that's been used forever for RNA data, RNA-seq or proteomics. It's been used forever. So whenever in doubt, try to use software that's been around for a long time. And so Limpa is the proteomics version of Limma, and I think the name is just hilarious. So like I think it's just one of the most hilarious names for proteomics I've ever seen. So anyway, this is my new favorite. It just came out less than a year ago, or less than when did the paper come out? The paper is currently in bioRxiv. I don't think it's been officially published yet, and it was posted on April of this year, 2025, so relatively new. You can find all of these links in the notes below the video. This is the GitHub site, so there's three. The GitHub site isn't very informative, but it sends you to the bioRxiv site, where you can read all about it, and you can also look at, the bioconductor site, sorry. Too many bios. So it will lead you to the bioconductor site, and then this will tell you how to install it, and then you can also go to the bioRxiv site to read all about how the software works. So I thought I'm kind of a little fuzzy on how it works, but I think I kind of understand it. So we're going to go through it in the paper, and we're going to go through some of the, I have an example project we're going to go through. So it should be pretty easy for you guys to do it on your own data. So the way I understand Limpa to work is that it takes data from DIA-NN, so it takes peptide level data. And let me see, it's easier to explain using the HTML. So what I like to do is, if you go to the bioconductor website, and I like to read this HTML analyzing mass spectrometry data with Limpa. And it goes in a little background, and it tells you about DIA-NN and where to get it. And it gives you a little quick start. So essentially what Limpa is doing is it's taking DIA-NN data, it's taking it in peptide level form, or I think it reads the peptide tables or the precursor tables from DIA-NN, and it's running a little function. And what this function does is that, and there's no graphs, here, I think that's it. It's doing some analysis or curve fitting. Basically what it's doing is it's taking the intensity of the peptides from the DIA-NN data and predicting how often you should see it. So for example, if you have peptide level data, and this is intensity data, and this is going to differ depending on what kind of instrument you have, whether you have an Orbitrap or a timsTOF, for example. Let's say you have a number 15, and that 15 you see, I don't know, in all of your samples globally, across all your samples, you see like 70% of the time, right? So, and then you have another expression value of 5, and you only see that like 20% of the time. And you have another expression value that's like 100, and you see that like 85% of the time. And so Limpa will build a curve for you, and that's what this function does, DPC fit, where it takes, or DPC, where it takes the Y peptide data from DIA-NN and fits a curve. And you can see it kind of here. And so this would be your log intensity of your peptide or precursor. I think it's, I don't know if it if it combines the precursors and the peptides. Remember, precursors are multiply charged ions, that there's usually two of them, +2 and +3 for peptide. And so you get the log intensity of whatever instrument you're running, and it fits a detection probability curve. So basically, essentially what this is saying is really, really weak intensity values from your mass spec are going to be more likely to disappear, right? And ones that are really intense, you're likely to see all the time. So if you have a really intense value, you're likely to see that every single time you run your sample. Things that are really low, you could see them 20% of the time or 30% of the time. So essentially, that's what that does. And then what it does from there is takes this into account and builds a protein level, sums up all of those based on the probabilities of those peptides into your proteins. And then it does some an MDS plot. I'll go over that in the code. It's essentially like a principal component analysis, but a little different. And then what it does is it takes your design, or you basically tell Limpa, these samples are in this group, these samples are in that group. And it does it does some curve fitting, which does some kind of analysis, which I'm kind of fuzzy about. But essentially what it does is it carries all of these errors forward, or potential errors forward, or likelihood of seeing the peptides forward, and then takes into account the groups. So for example, if you have like one set of conditions and all of your signals are like 100, and you see that all the time, and then another condition, those peptides are now missing, Limpa will tell you that that's most likely due to biology, right? Because these signals should be seen 98% of the time in all your samples, yet some of your groups, you don't see it at all. So Limpa will tell you, hey, this is most likely biology and not, a missing value. Whereas, on the contrary, if you have a group of proteins or peptides, I believe it's done on the protein level, that are like intensity of 5, and those are missing all the time, then it's most likely due, if you're missing all those in one condition, it's most likely due to random, just because it's below the detection limit. So think of these as a series of errors that you're propagating through the analysis. Like, is my intensity really intense? That's probably seen all the time. My intensity is really low. That can be missing just by chance. And then it takes into account the groups or the conditions. And then what you end up with afterwards is a series of protein level numbers, and those don't have any missing values anymore. So it fills those in based on the probabilities. And then it feeds all of that into Limma, and it uses this thing called, I think, VUMA. It's kind of, I don't know. I've read the paper a couple times. I'm still kind of fuzzy about it. Hopefully, once I figure it out more, I will post more about it. But let's go and look at how you actually run it. So what I did was, during our proteomics short course, we generated, I think, over 300 samples. So every year we give the new students, there's probably like 30 of them, urea and solution digest, an S-trap, and a magnetic bead digestion protocol. And we give each person 3 of those. And we have about 30 students a year, so we have about 100 samples per class. So we have about 300 total over 3 years. So this is the short course data from 2023 to 2025. I'll put the link to this. I don't know why you'd want to download it, but you could if you wanted to reproduce what I did. I'm probably eventually going to publish this eventually. It's kind of interesting what the results are. And so I searched all of this on my high-performance computing cluster. So I took all 287 samples, searched them with DIA-NN on my HPC cluster, and then the output is here, along with the code I'm using from Limpa. All right, so let's go through it. Oh, and by the way, I have a top hat on today because we had the Genome Center Halloween Symposium, and this is all I had to dress up with. So anyway, that's why I'm wearing it today. Okay, let's go through the code. We'll minimize this a little bit. And so this code, you can adapt mine. Wait a minute, stop. I don't even know what that is. you can actually take my code or use the code from, I think I got it from the HTML thing from Limpa. Okay, so I'm using RStudio. If you don't know what RStudio is, it's really easy to install. Just Google search RStudio. You'll want to download the most recent version of R. Limpa actually needs, I think, R version 4.51 or later, which is one of the relatively newer ones. So if you try to install it and you have an old version of R, you're going to get an error. Okay, so this kind of just, this is an R Markdown file, which is what I like to use instead of regular just R code, because it's easy to knit it into an HTML document or a PDF. So I prefer this, and it's easy to follow along. So all this is text that kind of explains what you're doing, and then little chunks of code. And you could run each little chunk of code by hitting this little arrow, or go up here and run codes below where your cursor is or above, or it's actually really, really useful. Okay. All right, so what we do is we give a little overview of Limpa and where it comes from and where this code came from. This installs all the packages you need. So if you load this in your RStudio, it should load everything. R is a little funky sometimes, but it should load all the packages you need to do the analysis, like Limpa and Lemma and complex heat map, which I got from our famed statistician here, Blythe. Hopefully I'll have her on a video soon. So she gave another, she usually teaches the Lemma part of our short course, and she does a great job, and she recommended using complex heat map, which is, I adapted her code for this. So it does all of that. Make sure you have all the tables installed, and then it actually puts those, turns on the libraries once you install it, or make sure you use them, or loads the libraries. Okay. Now, this part of the code is where you tell it where the report is from DIA-NN. So it's relatively new, right? So it'll read the report of the Parquet file from DIA-NN, which is great. So it'll read the output report from DIA-NN. So you just point it to your report.parquet. And then it'll also read your annotation file. So this is what tells which sample goes to what condition. All right. This can take a while, I think, this part. No, this part doesn't. So it takes this just defines where your Parquet file is, and this just defines where your annotation file is. That's right. That's how I set it up in the code. So this is just defines the variable. So for example, your report file variable is going to point to report.parquet, and it knows where you are because you've saved your markdown file in the same directory as your Parquet file. So you don't have to set the working directory in this code. All right, so then it does this function where it has this function read DIA-NN. This is from the Limpa package, and reads in all of the stuff from DIA-NN, the Parquet file, and puts it in this DAT. And then you can do some filtering on the DAT if you want. One of these doesn't work very well. I'm trying to figure out why, but you can get rid of non-proteotypic peptides. You could filter away compound proteins, and I think those are protein groups. So if you want to filter away, I don't know why you'd want to do that. I wouldn't do that at all. I didn't do it in this code. And you could filter away protein groups that are only single peptides. I didn't do that either. So I don't think I did any of these. I would recommend you not doing them either. If you do them, keep an eye out for, let's see, where is it? The DAT here. Keep an eye out for the number of proteins, and that it will go down dramatically. So anyway, this reads in your DIA-NN results. I would not do these, but you can experiment with them if you want. Then it will output, what this does is it outputs the column names as a text file. And why that's important, and I think it's still important with Limpa is the same way as Lemma, is they have to be in the same order. So I think that's a big thing with Lemma. So your sample names have to be in the same order as the columns in DIA-NN. So I have some code in there that checks for that. All right. and then this takes a long time. I think in this data set it took hours, like maybe 4 or 5 hours, but this is a really, really large data set. So it does this DPC function on your DAT, and your DAT comes from your DIA-NN file, and then it fits this curve to it and then plots it. So let's see, this is your curve. It looks like a pretty funky curve if you ask me. I guess it kind of doesn't look like, I don't know, is that fitted? I don't know how to read this. It looks kind of funky, but anyway, we're gonna go for it for now. So this is your log intensity of your instrument, so of your peptides or precursors, I assume. And then this is your detection probability of actually seeing that. So you could see in my data set, the log intensity of 20, it predicted it would be seen all the time. And a log intensity of like 7 would be seen hardly 0. And this kind of looks like a flat wall. I don't know. It kind of follows this curve, I guess. And I don't understand where this comes from. That looks kind of weird. I want to get some clarification on this. But anyway, this is the curve it built. I think so. This is the curve, and this is the data it comes from. I don't know. I have to figure that out. Okay. So anyway, now we have the probabilities based on the detection in the mass spectrometer. So now Limpa knows the probabilities of every peptide, how often we should see it. All right. And now we tell it what our conditions are. So I define my annotation table up here. Right. Let's see, where is it? Right here. So that's my joint annotation. And I'll put that that's in the BioShare. You can kind of see what it looks like. So it builds that, and it calls that targets. Probably that's not a great name for it. I don't know. You could probably change it to conditions or something. And then what I do is reorder everything. It should match already, but if it doesn't, it reorders it to match the DIA-NN tables. This I got from Blyce Limma analysis, and I assume it's the same way. So it makes sure the order of the columns in the targets matches the order of the rows in the annotation matches the order of the columns and the DIA-NN output. I believe that's what it does. And it does some checking. So if it's wrong, it'll tell you. And then that's pretty important. And if you screw that up, I believe your data will be scrambled. So that's why I put these checks in there. But if you're a Limma expert, let me know in the comments. And I will post Blyce Limma tutorial too, which I use to make this. All right. So we have three variables. Some of this may not be important, but some of the variables is I have a group, and that's the whether I did a magnetic bead digest, or urea digest, or an S-trap digest. And then I have the year. So the year the course was done, 2023, 24, 25. So I have 3 years worth of data. And I also have the students' initials. So because there's the student did multiple tests, we have to compensate for that in the design, and that's where Limma is really, really nice. So Limma will make these linear models, and you could add all of these different variables to help control for it. So for example, it uses the model matrix in the design, and I'm taking into account the group, which is the condition, like the digest and what kind of digest I use, what year it was done, and what the student did. All right, and then it kind of makes this design matrix, and this is the same as Limma, so it kind of tells the software what kind of stuff to do. And I have 287, I think. Total samples, and that's just the name of the sample. So we digested we analyzed 400 nanograms of each sample, which is a mouse liver. All right, and then we do these MDS plots, which is multidimensional scaling plots, and I think they're pretty similar to principal component analysis plots, but they take into account the Limpa tutorial says they take into account the errors of what you should be seeing. And you can see mine right here. So if you run this code, it should generate similar plots for you based on your code. So I did this this is based on group. So these are the 3 different digest conditions, I think. So I think this is S-trap and beads and urea. And then let's see, what are the other ones? This one is by group. So yeah, the 3 different conditions. This is by year, 23, 24, and 25. And I guess there is some clustering, but not too much. It looks to be mostly clustered by group. And so this is by year. And then this is by student, which didn't really make any sense, but I'd do it anyway. So there's only 1 student in each year, so I don't know. All right. So then we make the contrast, and this is very similar to Limma, so you could watch a Limma tutorial, or Blyce, look at Blyce tutorial too. And so we use this function called make contrasts, and that kind of basically tells it what differential expression to do. So this, we do 3, so this compares the urea to the magnetic beads, and this compares the S-trap to the beads, and this compares the S-trap to urea. And then what it does is it takes the protein level data, which now will not have any missing values, because it kind of filled in the missing values based on the probabilities based on the intensities, and now takes into account the design. So this is important. So now that it knows what conditions are what, it will try to figure out, using modeling, like what's most likely due to be random chance of just missing, and what's most likely to be there for real, like large intensities that are seen all the time. You should see it all the time. And so it takes those probabilities and those errors and weighs them in the formula. So it gives more credence, I think, to things that should be seen all the time. I think that's the gist of it. And so it does that, and that's what this DPC-DE function does, and this contrast fit and this eBayes, and those are part of Limma. But it uses this thing called VUMA, and I think that was made for RNA-seq. And then these are all the proteins, I think, in the experiment based on the predictor of how often we see them. And this takes into account the errors of the peptide. So think about this as it takes all of these errors and all of these probabilities that we should see them and keeps rolling them forward, right? This is how I understand it anyway. All right, now that we have all this data, and we have all our protein data without any missing values, we don't have to worry about missing values. We have all the probabilities of how often we should see everything, and we start making some plots. And I used complex heat map and ChatGPT to help me make some volcano plots, and they turned out really pretty. You can do your log fold change cutoff here. You can set your FDR cutoff on the Q value. You could how many proteins you want to label for each, and how many proteins you want to put on your heat map. So I don't think heat maps make much sense if you have like hundreds. We've all seen those like crazy heat maps that you can't even read. So I don't like those. So I limit them to 20, and we do that for each condition. And this is just like a function that ChatGPT helped me write. And you can just cut and paste this into your code, which without much changing, I think. And then over here, it actually runs that code it just made. And what this does, I'll move this down. What this does is does the volcano plots for, this is the beads versus urea. So these are the proteins that are upregulated in I believe the beads or urea. I forgot which was on the top and which was on the bottom. These are the ones that go up, and these are the ones that are changing. And then we also have a heat map. I believe these are a little different. So these are the top 20 proteins that were differentially expressed in the beads versus urea. And I think this is a much easier to read heat map. And so what I like to look for is, you see how they cluster by year, more or less. There's a little green mark here, but usually your data should cluster by your condition on your heat map, which is good. If it's all scrambled, then you know, like for example, do you see how the year doesn't cluster, which is what we want to see, right? So if like I had a variable like 1 year the urea digest worked completely differently than the next year, you would see it cluster, but it doesn't. And so this is really nice. So it's not clustering by year, but it's clustering by condition. And this is one of the reasons I like to use this complex heat map. It's really pretty, and you can get multiple things clustering together. And so you could kind of see, for example, like the log, and these are Z values. And so you can see how they're going down in the beads, this protein, and up in the S-trap and urea. So red is up and Z is down, and you can see the years. So that's kind of nice. So we did that all for beads versus urea versus beads, S-trap versus beads, and S-trap versus urea. And remember, this is 3 years worth of data, so 300 samples total. Oh, and something I should have told you is when I do the model, I told it to take into account the students, and that is done, I think, under the fit command. I think, where is that? It was done under, let's see, where is it? Somewhere. Let's see, it was probably done up here. Where is it? Somehow I put into account the student. It was done up here because we have to take into that account. Yeah, here we go. So under the model matrix, it takes into account the student and the year. So that's important because the student did 3 different tests. So there's a variable related to 3 tests, and that's the student. So it takes that into account. Okay, and then let's see. I used some functions from Limpa to see if the students had any effect. I'm pretty sure they wouldn't, but I use this thing called variance partitioning, where it tells you what is the most likelihood responsible for the variance between the different variables. So for example, the group is 81% of the variance, and the students are 18, which I guess is kind of, it's a little high, like 18%, but 81% is the actual the sample prep. I didn't do year. Maybe I should have done year. Then I also do, this is unnecessary, but then I just did a chi-square test to see if the students had any significant role in the analysis, and they didn't. So anyway, you can pretty much ignore the students that are doing the same tests. Okay. And that's just variance partition. I just was screwing around. You can ignore that. And then it outputs the table and the matrix with all of the p-values, and all of this will show up in your directory. And so I think if you just use this code and put your data in here, it should be really easy to modify. My rule of thumb, I also like MSDAP, but my rule of thumb is that, Limma's been around forever. All the statisticians pretty much trust it, I think. At least the statisticians here do. And so Limpa is based on Limma, and even though it's pretty new, my favorite statistician here, Blythe, really likes it. So I think it's pretty good. I would say if you want to do differential expression and you want to be pretty sure you're doing it correctly, I would try Limpa. And plus, it makes pretty pictures, and you can knit it into a PDF or a Word document or HTML. It makes it really easy to send to your collaborators. It makes it really easy to reproduce your results because it's all in your code. And so I would totally recommend this. And all you need is, it's free, and DIA-NN is free if you're an academic, so you could do the whole workflow for free. You don't have to pay anybody. And so anyway, I would recommend Limpa. I'm going to put all these links in below the video when I post it. Let me know what you think, and let me know if you run it on your data, if it worked for you. So it's worked on the data I've run it on so far. So I think this is a pretty good software, so I recommend it. Okay, all right, bye everybody. I'll try to do, I wanted to do a more recent version of DIA-NN. It hasn't really changed much from my video 2 years ago. There's some under the hood stuff that's changed I can get into, but running it's pretty similar. So anyway, I'm going to try to do that next. All right, thanks everybody. I'll see you guys later.